Our topic is subject is manufacturing processes 2, that is continued. Module number 2, mechanics of machining, we are continuing, and under mechanics of machining today our topic will be cutting forces and power required in machining. Now, today's 8th lecture on this. Today we shall cover machining forces and merchant circle diagram, which deals with cutting forces. Now, what are the contents subject today? Specific instructional objectives to enable the students at the end of this lecture ascertain the benefits and state the purposes of determining cutting forces. Why should you learn cutting force? Why should you like to know the cutting forces? What is the utility? Next, identify the cutting force components and conceive their significance in machining. Third, develop merchant circle diagram and show the forces contained into that. And fourth, illustrate advantageous uses of merchant circle diagram. Now, first let us see the benefits and purposes of determining cutting forces. Why one should learn this subject? Why should we try to determine either theoretically or experimentally the cutting forces? Before we do that, we should know that what major aspects we are interested in about the cutting force. The aspects of the cutting force is concerned, the magnitude of the cutting force, that is most important. Then locations and directions of actions of those cutting forces in the machines, nature or pattern of the cutting force, whether static or dynamic. If dynamic, then what is the frequency and amplitude. Now, the determination of the cutting forces facilitate or are needed for. This is actually advantages or the purposes of determining the cutting force. How does it help us, this information? Knowing the cutting forces enable engineers or anybody estimation of cutting power consumption. You know, cutting for power consumption is a major issue for everybody. It has to be minimum as far as possible. Now, in cutting some power is consumed, that has to be known, and then we should act accordingly. Estimation of cutting power consumption for selection of motor. You know, a machine tools are driven by some motors, and what should be the specification of that motor? When we design a machine tool, we design the power drive, and in the power drive we have to select one, say motor. What should be the power of the motor and what should be the RPM or speed of the motor, and that requires knowing the cutting force. Structural design of machine tool, fixture and the tool system. What is mean by design of a machine element? By design of machinery element, we understand, if you remember, that say this is the machine element we have to design, and first of all we have to select the materials and then determine the dimension of this component such that this component does not fail due to stresses caused by the forces acting on the component during its functioning. So, the forces have to be known which will cause stress, then we shall see that stress does not exceed the strength. So, magnitude of the stress, forces, the direction and location of the forces have to be known to determine the stresses. Evaluate role of the machining parameters on cutting force. As I already said, you also understand that attempt should be made to reduce the cutting force, which is detrimental, because cutting forces cause more power consumption and dimensional inaccuracy and vibration. So, we have to control cutting force, but not at the cost of productivity. But how can we reduce the force? Unless we know what factors govern or affect the cutting force. Therefore, we have to evaluate the role of the machining parameters on cutting forces. What do you mean by machining parameters? Say process parameters, cutting velocity, feed and depth of cut. If we change or increase the velocity, feed and depth of cut, what will the effect of the force? And this effect on the force have to be evaluated by measurement on knowing the cutting force. Then these tool parameters, the cutting tool material and the tool geometry, which play a role on the cutting forces. Then environmental parameters like say cutting fluid application or any special technique. So, we have to know about the cutting forces. Study machinability characteristics of the work material. Now, the work material has got a certain strength or shear strength. More the strength the material possesses, more amount of force will be developed and more amount of energy will be required. But the classical property of the material that we observe may not be maintained in the cutting condition. Suppose the shear strength of the work material may be widely changed during the cutting process or cutting condition. So, we have to know the actual cutting force in the cutting condition, and if we know from this cutting force we can study or understand the behavior of the material with respect to machinability. Condition monitoring of the cutting tool and machine tool. Now, during machining the cutting tool undergoes gradual wear and tear. Sometimes it may undergo very rapid plastic deformation because of high temperature and pressure. Whatever be the case, the tool becomes dull, and this is very undesirable. It becomes too dull, then we have to replace it. We have to withdraw the cutting tool and replace it immediately. But how do you know that the tool has worn out? We cannot take it out time to time, stopping the production. So, we have to continuously monitor or measure the cutting force. From the change in the magnitude and pattern of the cutting force, one can understand the condition of the cutting tool or even the machine tool. If the machine tool is defective or has some problem, then cutting force pattern will change. So, we should continuously measure or look into the variation in the cutting force magnitude and pattern, or the static or dynamic, like that. So, for these reasons and for the purposes, the cutting forces have to be known offline and online always. Now, machining forces and their significance. Let us say cutting force and its components in machining by single point tools. Now, there are different types of cutting tools. They are grouped like single point cutting tool and multi point cutting tool. Single point cutting tool are characterized by where there is only one main cutting edge, and on that cutting edge there is only one force. For example, say single point turning tool, shaping, planing, boring, these are the slotting, these are the single point cutting tools. And multi point cutting tools, drill has got two cutting edges, and milling cutters have got multiple teeth, they are different. So, first we shall discuss about single point cutting tool, the force analysis of single point cutting tools. Say turning, this is the turning process. Okay. This is the workpiece which is subjected to rotation, that is cutting velocity, and the tool moves in this direction, that is feed motion. So, this is the contact area. Now, at this point there will be only one force developed. As I said, the single point cutting tool is characterized by having only one cutting force. This is the cutting force denoted by R. Okay. And this is resolved into three components: one tangential, say Pz, other one in the axial direction along the axis of the job, this is called Px, and another transverse or in y direction called Py. So, vector summation of Px, Py and Pz will be the resultant force R. Now, you can see in this diagram also, on the right hand side diagram, this is the top view or the reference plane view of the cutting process, turning process, and this is the cutting motion of the job, and this is the feed motion, and this is the cutting point. Okay. At this point, if you take a section along the orthogonal plane, this is orthogonal plane and this is orthogonal view of the cutting process, this is the uncut chip that flows into the form of the chip. Okay. And here on the cutting tool there will be one force acting Pz, that is along the direction of cutting velocity vector, another one Pxy that will act along over the reference plane, because this is the reference plane, and this will be shifted along this is also along the orthogonal plane. So, Pxy will be perpendicular to Pz and will act along orthogonal plane and over the reference plane. Now, this Pxy is again resolved into two components, Px in the direction of feed direction and another Py called transverse force, Py in the opposite direction, and this angle is phi. So, there is only one force which is resolved into two components, Pz and Pxy. Pxy is again plus resolved into Px and Py. So, the resultant force R is equal to Px plus Py plus Pz, the vector summation. So, this force R is resolved into 3 components, and these 3 directions are right angle to each other. There should be, and this axis x, y, z, they are the axis of the machine tool. So, these are all in machine reference system, so that we can easily measure and analyze these forces and identify the forces. Now, what are the significance of these forces? What is the contribution or role of the forces? As you see, this force Pz, the force component Pz, that is the largest in magnitude amongst Px, Py, Pz. So, that contributes maximum, and it acts along the direction of the cutting velocity. So, this force multiplied by this Pz multiplied by the velocity will give you the cutting power consumption. So, this is also called power component, main component or power component of the cutting force, this Pz. Then comes Py. Now, Py maybe is usually smaller than Pz. As such, Pxy is around half or less than Pz generally. So, it is small, and Pxy is further resolved into Py, which may be quite small, but since it acts in a transverse direction of the cylinder rod, this will create lot of elastic deformation of the workpiece, tool, headstock, tailstock, and all the parts of the machine, and will result in dimensional inaccuracy and cause lot of vibration. So, it is very detrimental, Py. Px is least important, least significant, because in this direction the machine is rigid. As such, Px is small in magnitude, and secondly, Px acts in the direction where the machine fixture toolwork system is quite rigid. So, you understand the significance of all these force components in turning process. Next comes to drilling, cutting forces in drilling operation. Now, as I told you, the drill is a cutting tool which has got 2 main cutting edges. This is one main cutting edge, this is another main cutting edge, connected by one small chisel edge, intermediate chisel edge. Now, say it will have therefore 2 cutting forces, and say origin, suppose this is the point taken arbitrarily on the main cutting edge. So, there will be a force, tangential force Pt1, and similarly there will be another tangential force Pt2. So, they are tangent to the circle here, and this Pt1 and Pt2 will be same in magnitude if the tool geometry are symmetrical and perfect. Now, this tangential force multiplied by this distance will give you the torque. So, if you want to determine the torque, then this Pt1 has to be multiplied by this distance. So, the average diameter, all right, or you can say d by 2 if this is the diameter of the drill. Now, so this Pt multiply any one, say Pt1 into say d by 2, this much is approximately d by 2, will give you the torque. This is equal to the torque, which is essential for design of the cutting tool, spindle, bearings, and so on. And then power consumption, what is power consumption? Pc, this is the 2 pi T n. What is n? N is the RPM of the drill, the rotating speed of the drill. So, and T is the torque. So, this Pt1 and Pt2 are very important, they are very large in magnitude, quite large in magnitude, as well as these are the power component, and this is basically the Pt1, Pt2 are equivalent to Pz in case of turning. This is equivalent to Pz in case of turning, tangential force of the main component, and this helps you get the torque as well as the power consumption. Now, come to the other force. So, on the there will be 2 more forces acting perpendicular to Pt1 and Pt2 and along the rake surface or flute. So, this is one force Pxy1, and this is another force almost perpendicular to the cutting edge and working in the face plane. This force will be resolved into 2 components, Px1 along the axis of the drill and Py1 in a radial direction. Similarly, this force component Pxy2, if we call it, will be resolved in 2 components, Px2 and Py2. Now, here you see that Px1 and Px2 are in the same direction, they are parallel. So, the total force in the axial direction will be sum of Px1 and Px2. Py1 and Py2 will be same in magnitude if the drill geometry is perfect or symmetrical, but you see that they are working in opposite direction. So, ideally Py1 and Py2 will nullify. So, as such they have got no significance, but if they are not equal because of imperfection in the tool geometry, then there will be one lateral force acting on the drill, and that is very harmful, may break the drill. In addition to that, so what is the significance of the forces? You see Pt1 and Pt2, here we see they are the very large in magnitude and they help in determining the torque as well as the power component. Px1 and Px2 work simultaneously in the same direction, so they give us the total axial force. Now, what about Pxe? This is Pxe here, all right. This is the force, axial force caused by the chisel edge. Now, the chisel edge is quite small, but the axial force produced by the small chisel edge Pxe is very, very large, maybe 60% of the total thrust force, and as such, so this Px will be added with Px1 and Px2 to get the total axial force. So, total axial force will be summation of Px1 plus Px2 plus Pxe. Now, Pxe alone can be 50 to 70% of the total force, because this small chisel edge removes the material by some stringent condition, like unfavorable condition like indentation or extrusion, because of very large negative break at that point and very low velocity, maybe 0 at the center. So, this is about the drilling force. Now, come to milling force, cutting forces in milling and their significance and use. Milling cutter can be different type, form milling cutter and profile sharpened cutter like this, but most of the milling cutters are profile sharpened cutter, and they are say different type, say slab milling cutter or plane milling cutter, which looks like a roller with a flutes, and end milling cutter and face milling cutter. Now, let us start with plane milling cutter with straight flute. Here the flutes are assumed to be straight parallel to the axis of the cutter, and this is a plane milling cutter having suppose 8 teeth, and we also consider for the beginning that only one tooth is engaged at a time. This is called single tooth engagement condition, only one tooth will be engaged at a time, but it can be made multi tooth engagement, and these cutting edges can be helical fluted, we shall discuss later on. But first let us consider the cutting forces due to the single tooth engagement of a plane milling cutter without helix. Now, at this point, suppose at this point, cutting point here, this cutting edge, one force will be tangential force Pt. This Pt is the tangential force, okay, tangent to the workpiece, and this is equivalent to Pz of turning. So, this is the most important force. There is another force that will be acting, the Pr. Pr is equivalent to Pxy of turning. Now, resultant of these two is R. R is a vector summation of this tangential force and the radial force Pr. Now, this force R can be resolved again for analysis further into a force Pz along the axis of the machine tool and another Py transverse direction, say Py. So, the main forces coming from the cutting process are the tangential force Pt and the radial force Pr, resultant of which is R. This can be resolved like Pz and Py in a transverse direction, and Z and Y are the axis of the machine tool. Now, what is the importance or significance of the forces? Here is the Pt, Pt is equivalent to Pz. This Pt when multiplied by the diameter, half the diameter of the cutter, say radius, this will give you the torque, and the torque is necessary to be determined for design of the cutter, cutting tool, design of the milling arbor, design of the spindle, design of the gearbox, and so on. This PT 2 pi T n, this give us the power consumption. So, what will the power consumption? That will depend upon the torque, and torque will depend upon the tangential force PT. So, PT is one hand, is very large in larger component. So, it is important PT, and it is a power component. It helps in determining the torque for design of the machine tool components and the power consumption. PR is also important because the PR, it acts radially. So, this will cause bending on the milling arbor, therefore, this will also utilized for design of the machine tool. Now, result of this tool is split into PZ and PY. So, PY and PZ will be utilized and very important for design of the machine tool and cutting tool holders and any fixtures and all these things. So, these are the significance of these cutting tools. Now, as I told that there can be multi-tooth engagement. So, number more than one cutting edges can be involved. In that case, what shall we do? In case of multi-tooth engagement, they say the torque will be equal to PT1 or I say plus PT I minus 1, say I minus 1 plus PT, if there are 3 PT I minus 2 and so on. Say one cutting edge will be here, and for every cutting tooth engaged there will be a force PT, and that is a vector quantity. But when this will be multiplied, by the diameter, half the diameter, then this will give us the total torque. So, total torque will be given by just a minute, say total torque. Total torque will be equal to summation of the PTI, that is a tangential force, this multiplied by diameter by 2, this becomes a scalar quantity. And now you multiply this with the speed, angular speed, you will get the total power consumption. Then PZ, what is total PZ? PZ total, so that will be also equal to summation of PZI. I means any particular cutting edge, which will have different angle of engagement. This is called angle of engagement. Then similarly PY total will be summation of PYI. I means 1, 2, 3 depending upon the number of the cutting edges involved. Now, next is Merchant cycle diagram. Simply MCD, Merchant is a scientist who carried out lot of metal cutting research, and he is a professor and he did lot of work in research, R&D and industry, and he developed a beautiful method of dealing with the cutting forces involved in machining, and this will very helpful. You will gradually see that how is it constructed and how does it help the people to analyze and understand, to conceive or the conceptualize the cutting forces. So, now we shall deal with Merchant cycle diagram showing the cutting forces and their relations. Now, first is the construction. The construction of the MCD for orthogonal turning. Now, here a point has to be noted that this Merchant cycle diagram is a very unique method, is applicable for orthogonal cutting only. It is not applicable for oblique cutting. However, now what are the forces acting? Let us say, before we go into the Merchant cycle diagram, let us have a look into the forces acting on an outgoing chip. Let us consider that it is a machining orthogonal turning of a ductile metal producing continuous chip, and here we see that a chip, a segment of a chip coming out from the parent body and being separated along the shear plane. This is the shear plane, just after which it is getting separated. So, there is a slip between the parent body and the chip. So, a shear force will act in this direction, a shear force, and which will exceed the shear strength of the material, and it will be slipped out in this direction compared to the work material. Now, the PS, the shear force PS, this one is PS, shear force is accompanied by another force Pn. This is called force normal to the shear force. So, these are the two forces to be induced into the workpiece, all right, to accomplish machining. However, so the chip is subjected to two forces from the work side, one shear force PS, other one force Pn normal to the shear plane. So, from the job side, the chip is subjected to two forces. Now, the chip is coming out at a constant velocity. We can consider this chip, part of the chip or segment is in a state of equilibrium, because the velocity is constant. From the tool side, what forces are acting on the chip? One force is the friction force. When the chip comes out, it slides over the tool. So, there will be force acting in the opposite direction, friction force, and another force N normal to the chip coming from the tool. So, from the work side, the chip is subject to one shear force PS and one normal force Pn, and from this tool side it is subject to force F and friction force and N. Anyway, now what is significance of the forces and how do they help in constructing the motion cycle diagram? This PS and Pn, these are the forces to be provided into the workpiece for cutting action. This is the resultant force R. Okay. Now, this resultant force has to be induced into the workpiece. How? Through the cutting tool. So, there is another force R1 acting in the same direction, but in opposite sense, and they are action and reaction, R and R1. So, we can write that R is equal to R1. What is R? That is a resultant of, R is resultant of PS and Pn, vector summation about this. Now, this R1 again is resolved into two components. It is obtained, it is provided through two forces, one along friction F and N. Therefore, this R1 is equal to force F vector and force N vector. Now, mind that the force is only one. So, there will be only one force, either R or R1, any one we can consider. This only force in single point cutting like turning can be resolved into PS and Pn or F and N through the, now F and N is the forces resolved in coming from the cutting tool, PS and Pn induced into the workpiece. Now, this R1 we do not know the direction and magnitude. So, we have to measure it sometime. So, we have to resolve into two directions, known directions. This is PZ direction, that is cutting velocity vector, and another component perpendicular to that, PXY, which is in reference plane. This is in reference plane. So, this is one PXY and this is PZ. So, here you can see that this R is also equal to Pz plus Pxy, where you remember Pxy is equal to Px axial force plus Py transverse force. Now, if we clean it, now take how to, what is the Marchand circle diagram? It is a Marchand circle. Scientist Marchand drew a circle and produced a diagram for analysis of mechanics of machining. Now, here you take this R, as a diameter and draw a circle. Taking r as a diameter, draw a circle. Now, this point will pass through the point of intersection of PS, this is PS and PN, because it is 90 degree. Since it is 90 degrees, so this point will be situated on the periphery. Similarly, if you draw another circle as it is shown over here, taking R1 as a diameter, this is the circle, this will also contain this point, because this angle is 90 degree. This will also contain this point. So, this is 90 degree. Now, here you see in this circle, this PS and PN are contained as intercepts. End points of the forces are situated on the periphery. Similarly, the end points of F and N are situated on the periphery. Similarly, PXY and PZ. This, any one of this circle is called merchant circle, and the total diagram is called merchant circle diagram. Now, this all the forces can be shown in one circle. In the next, you see. Now, here you see the actual merchant circle diagram, where there is only one circle drawn as the resultant force R, as a single force, as a diameter, and in this circle all the force components concerned are contained as intercepts with their end points on the periphery. This force PS is very important, because this is the amount of force essential to cause chip separation or chip production, that is machining. PS cannot stay alone, so there will be inherently another force acting normal to this. So, PS and PN. Resultant is R. Now, this R is again resolved into two components, is F. Now, this force, friction force F, has been obtained into this by extending the rake surface, because the friction force acts in the rake surface. So, it is extended in this direction and contained as an intercept into the circle. So, this is the magnitude of the friction force, and normal force is this one, because F plus N vectorially is equal to R, and this is the friction angle eta. Now, if we resolve into the direction of velocity vector, so this is Pz, all right, and the other one is Pxy. So, this Pz and Pxy are normally obtained by measurement, and Ps, Pn, F and N, these are all function of the machining condition, and they can also be resolved from Pxy and Pz. Suppose if we know Pz and Pxy by measurement or by dynamometer, then we can draw this Pz in the with a proper scale. We have to choose a scale, say 200 Newton is equal to 1 centimeter, then 1000 Newton will be 5 centimeter, like that. You draw Pz first in the direction of the velocity vector, then Pxy normal to that according to the scale, join the tips and you get R. Taking R as the diameter, draw the circle, okay. Then you extend the surface, rake surface, you get F, join this line, you get N. Now, regarding PS, what is this angle? This is called shear angle. The shear angle has to be determined from other data. If we know shear angle, then we can draw this line, and this intercept will be PS, intercept circle, and the other intercept will represent Pn. This is how the forces can be determined. This will be discussed in more detail. Now, use of merchant circle diagram. How can you utilize it or exploit it? It not only enables only force analysis, it can help us further. You can see proper use of merchant circle diagram may enable, if you can use properly, determination of several other relevant forces, say PS, Pn, friction force F, normal force N, etc., from a few known forces, say Pz, Px or Py or Pxy, without much calculations. So, calculations is not much calculation not necessary. Simply by drawing the diagram, you can get the forces just by as an intercept multiplied by the scale or divided by the scale. Easy and quick evaluation of the coefficient of friction. Now, the machinability, whether machining is good or bad, is just by the chip tool interaction. that is the interaction at the chip and tool interface, like friction, built up edge formation, etc. Now, this friction force can be measured on fixed normal force N can be measured from the Martin cycle diagram, and ratio between F and N will give you the coefficient of friction, but this is apparent coefficient of friction, is not the real, but apparent coefficient of friction, just a ratio between F and N. So, this important information can be derived, because the friction is a measure of good machining or poor machining, can be obtained by measuring F and N, knowing if you know the values of F and N from Martin cycle diagram, then you can determine the friction, as well as you can also determine the dynamic yield shear strength of the work material. The work material has got certain shear strength, but under the cutting condition the shear strength may change because of strain rate, work hardening or stress strain hardening, like that, and we should be able to measure or know how does the material behave under the cutting condition, and that can be best assessed by the value of the force that will develop during actual machining. So, the behavior of the material under cutting condition and its dynamic yield shear strength can be determined from the cutting forces and using the Martin cycle diagram. Further, the development of equations relating the various forces in machining. Now, you know that some people are very strong in mathematics, they like to use equations and solve problems. Some people are very strong in graphics, method of drawing, sketching, and slightly reluctant about using, say, equations. For them, Martin cycle diagram is very good, but some people may not like to draw the Martin cycle, they like to use equations if available for calculations or analysis or determination of other forces from the known forces like Pz, Px, y. Now, even then, if you want, somebody wants to use the equations only to avoid Martin cycle diagram, that equations will be also developed from the Martin cycle diagram. So, Martin cycle diagram also helps in developing the equations which will be used to avoid Martin cycle diagram, and these equations will be shown later on. But limiting conditions for MCD, Martin cycle diagram. So, as you see, the Martin cycle diagram is a very good technique or a very beautiful diagram which enables very quick and easy determination of the forces involved in machining, but it has got certain limitations also. We should be careful about using it. It cannot be used universally under all machining conditions like oblique cutting. What are the constraints? Martin cycle diagram is valid, or you can apply it only for orthogonal cutting, when all the forces will be contained in the orthogonal plane, both Pz and Pxy, both Pz and Pxy will be contained in the orthogonal plane. There will be no force in the cutting edge direction or other direction. The ratio of friction force and the normal force gives apparent, this is apparent friction. This is apparent friction. This is not the real coefficient of friction. This is only simply the ratio. If you want to get the actual friction, then you have to do some more work. But however, it is very close to the coefficient of friction, which is an index of machinability or the characteristics of machining. So, this can be, so this Martin cycle diagram will give you only this ratio, that is apparent coefficient of friction, but not the actual. For that, some more work has to be, more analysis has to be done. Now, this Martin cycle diagram is valid for single shear plane theory. Now, what is single shear plane theory? The diagram that we draw, that is the cutting process, this is the cutting tool and this is the uncut layer, and this goes out in the form of chip. We assume that there is a shear plane, a single plane along which the deformation, the chip comes in this direction, then goes out in this direction. This velocity is very low, say chip velocity, and this is cutting velocity we see. Now, here the cutting velocity at high magnitude is immediately becomes Vf, low magnitude, within 0 time, almost 0 time. If the plane is a single shear plane, almost in 0 time, that is the deceleration, say deceleration r is equal to BC minus BF by tau. Now, if we take single shear plane, then this tau is almost 0, then R will be infinity. The deceleration, similarly strain rate, everything will be infinity, which is not really true, which cannot be. So, this single shear plane theory so this cannot be single shear plane theories. What is true is shear zone theory. What is shear zone theory? That if the tool is here and then the chip will deform over a region. So, this is the chip flow region, and this is the true picture of the flow. Of course, the thickness of the shear zone is very thin, and with increase in velocity this become thinner and thinner in the order of micron, say 50 micron, and we consider for convenience as a single shear plane. But this is a limitation, this is not true. So, this multi-cycle diagram, which assumes that the entire process is based on single shear. So, this is slightly approximate process. Now, let us see the utilization of this. A typical example of application of multi-cycle diagram. Now, you will learn how to utilize this multi-cycle diagram for solving problems, for analyzing, and for determining other components and so on. Suppose the values of the followings are given, some data are given for an orthogonal turning operation. Orthogonal turning, that means the chip flows along orthogonal plane. Now, what are the informations given? Suppose the process parameters like cutting velocity is known, the cutting velocity is known, feed is known, depth of cut is known. Tool geometry, here the lambda has to be 0, the inclination angle, otherwise it will not be orthogonal cutting. This nose radius should also be 0 for orthogonal cutting, and almost 0, not exactly 0. Gamma O rake angle should be known, and this principal cutting edge angle should also be known. These are, suppose these are given, say gamma 10 degree or phi 60 degree, like that. Environment, say cutting fluid. The environment means cutting fluid. Suppose we are not using cutting fluid or any, say, soluble oil. Cutting forces measured. So, by dynamometer we measure the forces Pz and Px or Py, or Pz, Px, Py, all these three forces we know the values from measurement. These are available, and the thickness of the chip that comes out after deformation. So, the thickness of the chip is also known. If not known, it has to be measured. Now, if with this information, suppose we have to determine some more information. What are these? The friction force F, normal force N, the apparent coefficient of friction at the chip tool interface, the shear force Ps, and the force Pn normal to that. So, these forces have to be determined from these known values. Yield shear strength tau s of the work material under the cutting condition, and cutting power Pc and specific energy Uc consumption. This has to be determined from this limited informations provided. Now, let us see how this can be done. Solution of this kind of problem. What we shall do? What we shall do? First of all, we shall do say we are solving the previous problem, all right. First you draw the cutting tool and the chip. So, this is the reference plane pi r, and this is the velocity vector V c. This is the cutting tool with rake angle, orthogonal rake, and this is orthogonal clearance alpha O. Now, this is the first part. Next part is we have to choose a scale. You choose a scale, say 200 Newton is equal to 1 centimeter. If we know the Pz, suppose Pz is 1000 millimeter, 1000 Newton, then it will be 5 centimeter. So, you take Pz here. Suppose this is the amount of Pz, which is given in length. Suppose it is Pz is 1000, sorry, Pz is equal to say 1000 Newton and scale is 200 Newton per centimeter. So, this intercept will be 5 centimeter. Similarly, you draw here Pxy. How do you get Pxy? Pxy you know that, or Px is equal to Pxy sin phi, or Py is equal to Pxy cosine phi. So, if we know Px or Py from the dynamometer or from the measurement and phi is already known, then we can determine Pxy. So, you put Pxy. Now, you join it, you get the force R like this. Okay. Now, let us go back to the previous. So, we get this P, this resultant, this R. Now, take this R as diameter, you draw the circle, the merge circle. Here what you have done, get Pxy from Px or Py as Pxy sin phi, draw tool and chip like this, the chip and the tool with the gamma O, draw Pz and Pxy that I have already described. Now, you draw this circle taking R as the diameter. Now, it is ready, the circle is ready. Now, you determine the forces one by one. Measure intercepts. Now, this is the rake surface. This is a rake surface which has to be extended until it meets over here. So, this is the length of the force F, friction force. Now, divide this length by the scale that you have chosen, that scale we have chosen, and then we get this force F. So, now here you see measure the intercept length and evaluate Fn. What is n? This length is measured and divided by the scale. Suppose it is 4 centimeters, so 400 Newton or 800 Newton. And what is mu a? This coefficient, apparent coefficient of friction. Either you take this, the friction angle eta as such, or the ratio of F and n will give you the value of friction. Now, how to determine the values of Ps and Pn? For Ps, which has to be drawn along the shear plane, and we must know the shear angle beta. Calculate beta, that is the orthogonal shear angle, from this equation, which is known, tan beta is equal to cosine gamma orthogonal rake zeta minus sin gamma divided by what is zeta? Chip reduction coefficient. Again we know chip reduction coefficient is equal to the ratio of the chip, thickness of the chip after cut, thickness of the chip before cut. A2 is measured or known. What about A1? A1 is equal to SO sin phi. SO is the feed given value and phi is also known. So, from known value you get A1, from known value of A2 and A1 determine zeta, put zeta here, gamma known, determine value of beta. From known value of beta you draw this shear angle, shear plane, this one, and this intercept is Ps. Now, join this one, you get Pn. So, you get Ps and Pn from this circle directly. So, you get all the forces F, N, mu and Ps, Pn directly without any calculation, no calculation needed. Now, we have to determine the shear strength of the work material. What is the shear strength of the work material? From Ps get tau s, shear strength of the work material. How? This shear force Ps is equal to shear strength of the material multiplied by the shear area. This is the shear area. What is meant by shear area? The shear area of the chip, cross section area of the chip along which shear takes place. Now, let us have a look into this. Suppose this is the orthogonal cutting, this is the cutting tool, this is the velocity vector, chip is flowing like this, this is shear plane, this is the workpiece, and this has got certain width. So, what is this? This is the width of cut B1, and this is the thickness of uncut layer, okay. And then this is the area along which this is the shear area along which the shear takes place. Now, this area is equal to this multiplied by this. So, this is a B, this is A, this is what is this? This is beta O. So, this length is A1 divided by sin beta O is this length, and this length is B1, that multiplied by B1, that is the shear area along which slip takes place. So, this is AS. Now, here you find that from PS the shear AS we have determined tau AS is equal to A1 B1 by sin beta, but A1 and B1 is equal to this A1 B1 is equal to T into SO. What is T? Depth of cut, and SO is the feed. So, from where we get AS and put AS value here, PS is already known from the merchant circle diagram, and then you get tau S. Now, get the power and power consumption and the specific energy requirement. Why power requirement is required? As I told you, that decides that how much power has to be provided into the machine tool through the motor, or it is also an index of machinability. If the power consumption is high, then machining is poor. So, our attempt should be to reduce the power consumption as far as possible, but not at the cost of productivity. But how shall we know that how much cutting power is consumed? This cutting power, this depends upon the force. This cutting power PC is equal to the product Pz into Vc. Actually, there is another component, that PC, the cutting power is equal to Pz into Vc plus feed force into feed velocity. The feed velocity is very, very low. Px is also small. So, this part can be neglected. So, PC, the cutting power, can be considered as almost equal to Pz into Vc. So, if we know the velocity is known already, if we know the cutting force Pz, then we can determine this Pc. So, Pz is known already, is given, velocity is also known. So, we get it directly. But what about this cutting power, specific energy consumption? What is specific energy consumption? That means amount of energy required by the work material to be removed, or amount of energy required for unit volume of metal removal, that is Pz into Vc, the amount of energy per unit time, and metal removal per unit time. So, this means amount of energy required per unit volume of metal removal. So, Pz cancels, so Pz TSO. So, this UC can also be determined by this process, but here we need knowing the cutting force. Now, let us see some example exercise. You will find here there are two exercises. I shall very quickly tell you the kind of exercise, the problems given or faced in, say, machining to utilize the merchant circle diagram, and how to exploit the merchant circle diagram to solve it very quickly and easily. Suppose the problem number 1. During machining, during turning ductile metal continuous chip by a tool of gamma rake angle or 10 degree, that is orthogonal cut, it was found that the cutting force Pz is 1000 Newton and Px is 400 Newton, Py 300 Newton. Why Px and P and zeta, chip reduction coefficient, is 2.5. Now, what has to be determined? Evaluate using merchant circle diagram the values of the force F, N, the coefficient of friction, then PS, Pn, etc. have to be determined. So, the problem is like this. So, what are given? The forces Px, Py, Pz, that is obtained possibly by dynamometer, and the chip reduction coefficient from the chip, and we have to determine the other forces. Now, solution. You have to first draw the Mercer circle diagram. First you draw the cutting tool, okay, with a 10 degree rake angle. So, this is the rake surface, and then you draw this direction of velocity vector and the Pz in this direction. How will you draw the Pz? The Pz is known 1000 Newton, that divided by scale. You have to select a scale first. So, select a scale 1 centimeter 200 Newton. Then what will be the value of Pz length? That is 1000 divided by 200, 5 centimeter. So, this is 5 centimeter. Then what about Pxy? This Pxy has to determine the Px and Py are known. So, you can take the root over Px square plus Py square, because phi is not known. So, you have to determine Pxy in this from this equation, because phi is not known. Now, what is this? 500 Newton approximately. If it is 500 Newton divided by scale 200, it makes say 2.5 centimeter. So, these two forces have been determined. Get the resultant force. Now, taking this as diameter, draw this circle called the Mercer circle. Now, pass on very quickly, things are very ready. Extend the rake surface, this is the intercept. So, this is friction force F, measure the length, put into the scale, that is divided by scale, or sorry, multiplied by the scale, that is suppose it is 3 centimeter multiplied by 200 is equal to 600, and this length you measure and multiply by the scale, and you get the force. Similarly, Ps, but before that you must know what is beta O. How will you get beta O? Beta O, tan beta O is equal to cos gamma divided by zeta minus sin gamma. So, gamma O are known. What is zeta? The value of zeta is given 2.5 already. So, you very quickly and easily determine beta O. Draw the shear plane, this is the intercept, measure the length, multiply this length by the scale. So, you get the force, and similarly this one intercept Pn, measure the length and multiply by the scale and get the value of force. You can see in the next part. So, what is the process? Solution I have already told you. Now, summary: draw Pz and Pxy. In this diagram, you draw Pz and Pxy, draw R as a resultant, extend the rake surface like this and get this intercept F, the F and N together, and so F and N, F has been determined, N, measure the length and multiply by the scale, you get it. Determine the shear angle beta O from this equation, tan beta cos gamma zeta minus sin gamma. Gamma is known, zeta is known, 2.5 given already. So, this is 23 determined. Draw this. So, this shear angle, this is shear angle, the shear plane. So, this is the intercept as I told you, and then from the Mercer circle diagram determine F. Suppose this F is equal to 3 centimeter multiplied by scale, so 600 Newton. Similarly, N will be, so it is suppose it is 4.6 centimeter multiplied by 200, 920 Newton. Mu is the friction, afferent coefficient of friction is the ratio of F and N. So, this is 0.67. So, Ps, the shear force this much, measure the length 3.4, multiply by the scale and you get 680. Then Pn, you know this length, say 4.3, multiplied by the scale, you get 806 Newton. So, this is how such kind of problem can be solved. Next time you will see that how this Mercer circle diagram can be used for develop the equations for solving the problems without using Mercer circle diagram in the next lecture. Thank you. This is the end.